Hey guys, today we're going to be learning about trigonometry. Now the word trigonometry basically means triangle measure, and it refers to the relationship between the sides and the angles of the triangle. Now there are three basic trigonometric functions. We have sine, cosine, and tangent as denoted here. Now sine, cosine, and tangent, when you write it, can be shortened to sin, cos, and tan. Now sine is the ratio of the sides, the opposite side over the hypotenuse. Cosine is the ratio of the adjacent side over the hypotenuse. And tangent is equal to the ratio of the opposite side to the adjacent side. Now how do you figure out what side is what? First of all, it all depends on the angle that is given and defined. So here we have this triangle. This symbol is called theta. Theta is usually used to represent a variable that represents an angle. So typically we see theta or x or any other symbol, and this represents some angle measure of the triangle. Now, if you were to draw a line directly from that angle to the side right across from it, that is always the opposite side. And as I wrote here, it is always directly across the angle that is given. The adjacent side is the side that is directly next to the angle and touching that angle. And the hypotenuse is always the longest side of the triangle, also most notably the diagonal. However, I don't necessarily use the diagonal to represent the hypotenuse because depending on the orientation of the triangle, it may be difficult to tell what is the diagonal, but it is always the longest side and directly across from the 90-degree angle. Now this is important as well. When we're looking for missing sides of a triangle, or when we're trying to determine trigonometric ratios using sine, cosine, and tangent, this always applies to 90-degree triangles or right triangles. So this is my right triangle. The hypotenuse is directly across from that right angle. The opposite side is directly across from the angle that is defined. And then the adjacent is basically the one left over, or the one that is touching the angle. So here we have this triangle as an example so that we can try that out. This is the angle that is defined, and we're being asked what would be the sine of theta. Sine is opposite over hypotenuse. And if you ever forget what are your ratios, we can use this here to kind of help us. SOHCAHTOA. You can just say it quickly, SOHCAHTOA, whatever. S stands for sine, OH, opposite over hypotenuse, C for cosine, adjacent over hypotenuse, T for tangent, opposite over adjacent. So sometimes you may find it helpful when you're doing work trying to find these trigonometric ratios to write this at the top of your paper and use it as a reference. So back to this example, we're looking for sine of theta. Sine of theta is going to equal to opposite over the hypotenuse. So we need to identify what is the opposite side and what is the hypotenuse. If this is my angle, my opposite side is the 2. And then my hypotenuse is the longest side, which as you can see, we have 2, 4, 7. So this is the hypotenuse, which again is also directly across from the 90 degrees. So sine of theta is going to equal to opposite, which is 2, over the hypotenuse, which is 7. And this would be my answer. So we discussed now these three basic trigonometric functions, but we also have another three trigonometric functions, which are the reciprocals. We have cosecant, secant, and cotangent. Their shortened version when you're working for cosecant would be CSC, for secant is SEC, and for cotangent is COT. Now these are, like I said, the reciprocal. So cosecant is the reciprocal of sine. Therefore, instead of opposite over hypotenuse, it would be hypotenuse over the opposite. Secant is the reciprocal of cosine. So instead of adjacent over hypotenuse, it's the hypotenuse over the adjacent. And cotangent is the reciprocal of tangent. So instead of opposite over adjacent, it's adjacent over the opposite. Which this is basically what you can follow in order to find these trigonometric functions. Or you can look at the values that you got for sine, cosine, and tangent, and then flip them, which is essentially what this means. 1 over sine means the reciprocal of sine. So whatever sine is, flip it around. Tangent and cotangent could also be described as quotient functions, meaning that for tangent, we can divide sine by cosine and get the value for tangent. Cotangent is cosine over sine, so you can divide cosine by sine, or whatever tangent is, and flip it. So the thing with trigonometric functions is that there are a lot of, these are called identities, that help us to evaluate them. Now let's look at this example that's given. We have this triangle where theta is here on the bottom, and then we have sides 3, 5, and 8. I always find it helpful to label the sides before I even begin, so that way I can determine what are my trigonometric functions. So if this is my angle, the one that is directly across, this is my opposite side. The longest side, this is my hypotenuse. And then this is the side that is next to the angle, so this would be the adjacent. So if I wanted to find the secant of theta, secant is hypotenuse over adjacent. As long as you know that secant is a reciprocal of cosine, you can look here if you write SOHCAHTOA and then instead of adjacent over hypotenuse, just flip it to hypotenuse over adjacent. So hypotenuse over adjacent, we would look at the hypotenuse, which is 8, over the adjacent, which is 3. And this would be my answer. Now for cotangent. Cotangent is the reciprocal of tangent. So instead of opposite over adjacent, it's the adjacent over the opposite. So we look here at my triangle, adjacent is 3, and the opposite is 5. And this would be my answer. Now let's have a look at how we would find all of the trigonometric ratios from a triangle. Here we have this triangle. Theta is over here. We have the 90 degrees. Let's label it before we determine all of these ratios. Here's my angle. So the side that is directly across, this is my opposite side. The one that is directly across from the 90 degrees, this is the hypotenuse. And the one that's left over and next to the angle is the adjacent side. Now sine, remember that this is SOHCAHTOA. Sine is opposite over the hypotenuse. So I look at the opposite and I put over the hypotenuse, which is 12 over 15. Now, all of these ratios should be simplified. And we can simplify 12 over 15 by dividing the numerator and the denominator by 3. 12 divided by 3 is 4, and 15 divided by 3 is 5. Now we look at cosine. Cosine is adjacent over the hypotenuse. So I look at the adjacent and the hypotenuse, and that is 9 over 15, which can be simplified to 3 over 5. Tangent is the opposite over the adjacent, so 12 over 9, which can also be simplified to 4 over 3. Now that we know sine, cosine, and tangent, I can figure out cosecant, secant, and cotangent by just flipping these fractions, since they are the reciprocal. Cosecant is the reciprocal of sine, so cosecant would be 5 over 4, since sine is 4 over 5. Now, just to make a note before I continue here, if you get confused as to which trigonometric function is the reciprocal of which, just think that S goes with C. So the reciprocal of sine is cosecant. Cosine goes with secant, S and C. So S and C's, they match together. So that's a little, I don't know, something that helped me in terms of remembering what is the reciprocal of what. So secant would be the reciprocal of cosine. Since cosine is 3 over 5, secant would be 5 over 3. Cotangent is the reciprocal of tangent. These are the two that are easiest to remember because they both have tangent in their names. So cotangent would be the reciprocal of 4 over 3, which is 3 over 4. And this would be all 6 of my trigonometric ratios. Now let's look at another triangle. In order for me to find all of these trigonometric ratios, I need all three sides. But what we have here are only two of the sides. So in order to find the third side, we would have to apply the Pythagorean theorem. Anytime that you are missing a side length of a right triangle, you can apply the Pythagorean theorem to find that third side. Now, as a reminder, this is the Pythagorean theorem. A squared plus b squared is equal to c squared, where a and b are the legs of the triangle and c is the hypotenuse. So both of these sides here, these are considered legs. These are the ones that come together and form the 90 degrees. And the hypotenuse, we already know, is the side that is directly across from the 90 degrees. So if I use the Pythagorean theorem, you can assign 14 as A or B, does not matter which one you call A and B, as long as C is always the hypotenuse. So I'm going to call 14 A, and this side here is B. So I'm going to solve for B, so that would be 14 squared plus B squared is equal to C squared, which is 22 squared. Now 14 squared is 196, plus B squared is equal to 22 squared, which is 484. Now we subtract the 196 to both sides, and we get that B squared is equal to 288. Then we square root. And we get that b is equal to the square root of 288. So now in order to continue working, whenever you have your square root, you always want to make sure that you're using the most simplified version of that square root. So we're going to break this down. And basically what you do is you look for two numbers that would multiply to give you 288. If you're ever unsure of where to start, if it's an even number, you know that 288 is divisible by 2, and 288 divided by 2 would give me 144. So that's one way of breaking down a large number. If it's an even number, you can always start off like this to start making it smaller. Now, 2 cannot be broken down further, but 144 can, which gives me 12 times 12. The whole point of breaking down a square root is to find the same number. These are a pair. So this 12 gets to go outside of the square root, where this 2 would have to stay inside. So b is going to equal to 12 times the square root of 2. And this is the simplified version of that square root. So again, just to make sure, pairs go outside of the square root, and individual numbers would stay inside of the square root. So b is equal to 12 square root of 2. Now I'm going to label what is opposite, adjacent, and the hypotenuse. Here's my angle. The side directly opposite is the opposite side. The one that is directly across from the 90 degrees, this is my hypotenuse. And then b, which I solved for, this is my adjacent side. And now we're ready to find our trigonometric ratios. Sine is opposite over hypotenuse, so 14 over 22, both of which can be simplified by 2, so that would give me 7 over 11. Now for cosine. Cosine is the adjacent over the hypotenuse, so we have 12 square root of 2 over 22. Now when you have a fraction like this, you can simplify the numbers that are outside of the square root. 12 over 22 can be simplified by 2, which gives me 6 square root of 2 over 11. And you leave the square root by itself. So what's important to note about square roots and doing any kind of operations that have like a mixed number like this is you can simplify numbers on the outside, and you can also simplify if you have a square root in the numerator and the denominator. So basically just don't mix inside with outside. Tangent is opposite over the adjacent. So 14 over 12 square root of 2. Now again, I know that I can simplify this. The outsides here, 14 and 12, can be simplified by 2, which is 7 over 6 square root of 2. Now, what's important to remember is you can never have a square root in the denominator. That's just a no-no, okay? Simply because a square root is, if you leave it inside the square root, that is an irrational number. If you put the square root of 2 into the calculator, you're going to get a decimal that goes on forever and ever. So what we have to do is take that number and rationalize it, much like how we've done in the past. So you look at whatever is in the denominator, the square root, and you're going to multiply both the numerator and the denominator by that square root. That way, when I do that, in my numerator, remember we cannot mix, this is not the square root of 14. 7 times the square root of 2 is just 7 square root of 2. But in the denominator, we have the 6, and then the square root of 2 times the square root of 2, which is the square root of 4. See, that I can multiply because they're both inside of the square root. But the square root of 4 we know is 2. So this is 7 square root of 2 over 6 times 2, which is 12. So that would be my final answer for tangent, would be 7 square root of 2 over 12. So we can never have, like I said, a square root in the denominator. If you do, you have to rationalize. And I have that here in blue in case you forget. Now cosecant is the reciprocal of sine. So instead of 7 over 11, the cosecant would be 11 over 7. Secant is the reciprocal of cosine, which if I flip that, I would get 11 over 6 square root of 2, which I cannot have since I have the square root in the denominator. So that means that I'll have to rationalize by multiplying the square root of 2 over the square root of 2, which would give me 11 square root of 2 over 6 times the square root of 4, which is 2. So 6 times 2 is 12. And that would be my secant. Now cotangent is the reciprocal of tangent. Now here's a little shortcut for you. Instead of just flipping our final answer for tangent, which would give us a radical in the denominator, we can flip the one that we got before we rationalized. And that way that would eliminate having to rationalize yet again. So my cotangent would be 6 square root of 2 over 7. Now, if you forget to do this, that's totally okay. If you end up flipping 7 square root of 2 over 12, you get 12 over 7 square root of 2, which then you would have to rationalize. So we would multiply square root of 2 to both the numerator and the denominator. And we would get 12 square root of 2 over 7 times 2, right? You can think about it as this is the square root of 4, which is 2, or square root of 2 times the square root of 2, the square roots would just cancel. So that's 7 times 2, which is 14. And then we can simplify both of these numbers here by 2, which is 6 square root of 2 over 7. And you see that it gives us the exact same answer. So whichever way you prefer to work out that cotangent, if you have, or any trigonometric function with the radical, is up to you. Now we're going to see how to find the rest of the trigonometric ratios if you're already given one. In this example, it says if the cosine of theta is equal to 2 over 5, find the exact values of the 5 remaining trigonometric functions for the acute angle theta. So here it says, first start off by drawing a diagram of the triangle. It does not matter how you choose to draw your triangle. I just put this as a template. Okay, you can have it facing the other way, you can have it upside, it doesn't matter. You assign theta somewhere. Again, does not matter. Now we are told that the cosine of theta is going to equal to 2 over 5. And if you keep in mind SOHCAHTOA, right, cosine is adjacent over the hypotenuse. So that means that 2 is the adjacent side and 5 is the hypotenuse. So I'm going to label that accordingly. This one here, this is my opposite side, this is my hypotenuse, and this is my adjacent. The 2 is the adjacent, and 5 is the hypotenuse. So I'm missing here the opposite side. So in order to find this, remember that we're going to use the Pythagorean theorem, which is step 3. So we have one leg, which is 2 squared, is equal to, I'm looking for my other leg, so I'll call that b squared, is equal to my hypotenuse, which is 5, squared. This gives me 4 plus b squared is equal to 25. Subtract the 4. We get that b squared is equal to 21, and then we would square root. So b is equal to the square root of 21. If we can simplify the square root, we would. But the only two numbers that multiply to give you 21 are 7 and 3, which are not pairs. So we're going to leave it as the square root of 21. Now we're ready to find all of these trigonometric ratios. Sine is opposite over hypotenuse, so square root of 21 over 5. Cosine is adjacent over the hypotenuse, so 2 over 5. Tangent is opposite over adjacent, so square root of 21 over 2. Now to find the rest of these, we have to flip them. For cosecant is the reciprocal of sine, so I flip 5 over square root of 21. But again, I have this square root in the denominator, so I must rationalize, which gives me 5 square root of 21 over 21, since those square roots just cancel. Secant is the reciprocal of cosine. Since cosine is 2 over 5, that means that secant is 5 over 2. And cotangent is the reciprocal of tangent. So since tangent is the square root of 21 over 2, that means that cotangent is 2 over the square root of 21, which again, I must rationalize, which would give me 2 square root of 21 over 21. Let's try another one. We have here, if tangent is equal to 1/2, find the exact values of the 5 remaining trigonometric functions for the acute angle theta. So let's label these sides. Here's theta, so that means that this is my opposite side. This is my hypotenuse. And then this would be my adjacent. Tangent is 1/2, and according to SOHCAHTOA, the 1 would be the opposite side, so this is equal to 1, and 5 would be, and 2 would be my adjacent side. So what I'm missing here is the hypotenuse. So if I apply the Pythagorean theorem, I have the legs. Now I'm looking for c. So this would be 1 squared plus 2 squared is equal to c squared. 1 squared is 1, plus 2 squared is 4, is equal to c squared. 1 plus 4 is 5, so 5 is equal to c squared. That means that c is equal to the square root of 5, if you square root both sides to cancel out that exponent. So my hypotenuse is square root of 5. Now we're ready to find the rest of these trigonometric ratios. Sine is opposite over the hypotenuse, so 1 over the square root of 5, which we must rationalize. And when we do that, we get the square root of 5 over 5. Cosine is the adjacent over the hypotenuse, so 2 over square root of 5, which I would then have to rationalize, which would give me 2 square root of 5 over 5. Now for tangent, which is opposite, tangent was given, which is 1/2. But either way, you can still see it here, opposite over adjacent. Now cosecant is the reciprocal of sine, which we had to rationalize at the end. So what we can do is just flip the one before we rationalized. 1 over the square root of 5 is the square root of 5 over 1, or just the square root of 5. Now again, if you chose not to do that and you just chose to flip what we got for sine, then that would mean we would get 5 over the square root of 5, which then we would have to rationalize, which would give me 5 square root of 5 over 5, since those square roots would cancel. And then here, these 5's will cancel, leaving me just with the square root of 5. Secant is the reciprocal of cosine, which I also had to rationalize. So I can look at my original cosine, which was 2 over the square root of 5, and flip that one, and I get the square root of 5 over 2. Or like I said, you can flip what you got here for cosine as your final answer, and then rationalize that, and you would get the same exact answer. Cotangent is the reciprocal of tangent, so we would flip tangent. Tangent is 1/2, so the reciprocal would be 2 over 1 or just 2. And that's how you would find that. Now we're going to look at how to find missing sides for what's called a special right triangle. There are two types of special right triangles where we can figure out the relationship, and actually it's helpful to find the missing side if you have only one side given. See, in all of the examples that we've been doing, we've had two sides given, and the most that we'd had to do is find the third side. However, special right triangles are helpful if we're only given one side and we need the other two sides. So I'm going to show you where the rules for these special triangles come from, so that way maybe in case you forget what the rules are, you can go through this process to figure out those relationships. So a 45, 45, 90 triangle, that comes from a square. We know that all squares have equal sides. And if you draw a diagonal from one corner to the other, what you get is a 45, 45, 90 triangle for each one. And this is why. We know that all angles of a square are 90 degrees. And when you draw the diagonal, that acts as an angle bisector. So a bisector means that it cuts the angle in half. And half of 90 would be 45. So this angle is 45, and this angle is 45. Now to avoid confusion, I am going to use the letter L to represent the length of a leg or a side. So I'm going to call this L, because I don't know what that side is. And if you look here, right, you see these markings. In geometry, we learned that these markings mean that all of the sides are congruent. So if this is L, then that means that this must also be L, because it is my other leg. What we're missing now is to find the hypotenuse. And in order to find a missing side of a right triangle, we apply the Pythagorean theorem. So we have a squared plus b squared. So L squared plus L squared is going to equal to my hypotenuse squared. So I'll use h to represent the hypotenuse. If you add L squared plus L squared, that gives us 2L squared is equal to the hypotenuse squared. Square root both sides, what we end up with is that the hypotenuse is equal to, now here we have the square root of 2, which I cannot simplify, but L squared means that there are two L's. So I can move the L to the outside of the square root. So my h, my hypotenuse, is going to be the leg length times the square root of 2. So those are my rules. We have that the legs for a 45, 45, 90 are equal, and the hypotenuse is equal to the leg length times the square root of 2. Now let's look at the other type of special right triangle, which is a 30, 60, 90. And that comes from an equilateral triangle. An equilateral triangle means that this side is the same as this side is the same as this final side. Additionally, all of these angles here are 60 degrees. If I draw the altitude, right, this is called the altitude of the triangle, which is another fancy way of calling it the height of the triangle. If I draw in the height of an equilateral triangle, this creates what's called a perpendicular bisector, which acts also as an angle bisector for this angle here. So if this angle is 60 divided by 2, this would be 30 degrees. And so here we have a 30, 60, 90 triangle. So we're going to focus on this side here. I'm going to call this short leg here my L. Now, if this is half, because this side is equal to this side, then that means that the entire length here of this base is 2L, because it's L plus L. That means that this side here is 2L, and this side here is also 2L. So that takes care of my hypotenuse. Now what we're missing is the height of the triangle, which again, I can use the Pythagorean theorem in order to solve for that missing side. So I have now a leg and the hypotenuse. So I would set this up as L squared plus B squared, what I'm trying to solve for, is equal to my hypotenuse squared. When I apply this here, the square to the 2L, remember that you have to apply the exponent to both the 2 and the L, which gives me 4L squared. So to solve for B, I would have to first subtract this L squared over to the other side, which gives me B squared is equal to 3L squared. And then we square root both sides, which gives me that B is equal to L, because I can move that outside just like we did here in this other example, and then the square root of 3. So this would be the measurement for this side of the triangle. So that's where the rules come from. And just to kind of summarize, I've created here a little chart that has all of the rules for you. So this is the 30, 60, 90, where you have L is the short side, L square root of 3 is the long side, and 2L is the diagonal. And then in the 45, 45, 90, both legs are L, and the diagonal is L square root of 2. So let's see how we would apply this. Here we have a 45, 45, 90 triangle. So we have one leg length. So this is L. And what I like to do is I take my triangle and I label all of my sides with the rules so I know exactly what to do. Since this is a leg, this is also my leg here, so that's L. And then the diagonal here for my 45, 45, 90 is equal to L times the square root of 2. I use the side that's given to me. L is equal to the square root of 2, and I can answer the rest of this. See, y here is equal to L, so that means that y is 3 square root of 2. X is equal to L times the square root of 2. So I'm going to take my leg length, which is 3 square root of 2, and multiply that by square root of 2, which gives me 3 times 2, because those square roots would cancel, and I get 6. Let's try that with this one here. Now this one is a 30, 60, 90 triangle. And as you can see, this here, the 16, is across from my 90 degrees. So this 16 is the hypotenuse, which is equal, oops, sorry, I was looking at the wrong triangle, which is equal to 2L. If this is my 60 degrees, I look here at my rule, and my 60 degree, like the side that is across from the 60 degrees, is equal to L times the square root of 3. And then my short side here, the one that is across from the 30 degrees, is equal to L. So I'm going to use the equation that's given to solve for L. So that's usually your first thing to do, is when you're given these special right triangles, solve for L. And that'll help you to plug in L into the remaining sides to figure out what that measurement is. So if 16 is equal to 2L, we would divide by 2 to both sides, and we get that L is equal to 8. So here we have y is equal to L, so that means that y is 8. X is equal to L square root of 3, so that means that x would be 8 times the square root of 3. Let's try again. This is another 30, 60, 90 triangle. So I'm going to label all of my sides with the rules. The side that is directly across from the 30, that's L. This is my 90. The side that is directly across from the 90 is 2L. And the side that is directly across from the 60, this would be the 60, is equal to L square root of 3. So I'm going to use this equation here because I actually have that equal to a number to solve for L. So 12 is equal to L square root of 3. Divide square root of 3 to both sides. And we get that L is equal to 12 over the square root of 3. But remember that we learned we cannot have a square root in the denominator. So we're going to multiply by the square root of 3 over the square root of 3 to rationalize. And this gives me 12 square root of 3 over 3, which can be simplified to 4 square root of 3. So that is L. Now let's go ahead and label everything. X is 2L. So if I multiply L by 2, that's 2 times 4, which is 8 square root of 3. Y is just L, which is what we solved for. So that would be 4 square root of 3. Last one here, we have another 45, 45, 90 triangle. We're going to label all of these sides. This is the easiest one because the leg lengths are always just L. And my diagonal is equal to L square root of 2, as we can see here. So I'm going to use this equation now to solve for L. So 6 is equal to L square root of 2. Divide by the square root of 2. And we get that L is equal to 6 over the square root of 2, which now, of course, I have to rationalize. And that gives me 6 square root of 2 over 2, which can be simplified to 3 square root of 2. So that's L. That means that both x and y are 3 square root of 2. And that's using our special right triangles. Now the last thing that we're going to do, going back to trigonometry, so let me just reiterate. We use special right triangles if we are only given one side and the triangle has the angles either 30, 60, 90 or 45, 45, 90. And then we're going to now find the missing side length using trigonometry. That means that it is not a special right triangle and we're also just given only one side. So first what we're going to do is we're trying to find here this side length, which is x. So what we do is we label whatever was given to us. This is my angle. I have here 16, which is the opposite side. And I'm trying to solve for the hypotenuse, since this is the one that is across from the 90. Then I examine, okay, opposite and hypotenuse. And you have to think to yourself, what trig function uses opposite and hypotenuse? So again, you may find it helpful to write out SOHCAHTOA. The trig function that uses opposite and hypotenuse is sine. So we're going to set up an equation. This would be the sine of my angle. Here I'm actually given an angle, so 63 is going to equal to the opposite, which is 16 over x, the hypotenuse. In order to solve for x, because that's my goal, I would have to multiply x to both sides. Now the sine of 63, this is just a number. And we're going to get that in a bit. But first we're going to make sure we can set up the equation to solve for x. So this is x times the sine of 63 is equal to 16. To solve for x, we divide by the sine of 63 to both sides. So this is what x is equal to. And now what we're going to do is we need a calculator in order to get this. So I'm going to take out my calculator here. Now one thing that obviously you may not have this calculator, whatever calculator you have, you are going to need to check your mode. There sometimes is a mode button or a menu button of some kind. If you have questions on how to access this on your calculator, please reach out. But you're going to go into your mode and you're going to make sure that your angles are set to degrees. See here, what's blinking is radians, which is another unit of measurement that we'll discuss later on in the course. But that is just another unit of measurement for angles. So I'm going to select degrees. Now I'm going to set up this equation. We have 16 divided by the sine, and then it's going to open a parentheses, and you have to place your angle, which is 63. And this would be my answer, 17.957, etc., which I'm going to round to the nearest tenth. And if I round to the nearest tenth, it would be 18. And this is my answer. Let's try a couple more. We have here this missing side, x. So first I'm going to label what I have. The 55 degrees is my angle, and the side directly across is 29, so this would be my opposite. Now this one here is my hypotenuse, since it is the one that is across from the 90 degrees. So that means that x here is adjacent. Again, the trig function that uses opposite and adjacent is tangent. So I would set up first my tangent equation. The tangent of 55 is going to equal to my opposite, which is 29, over the adjacent, which is x. So for this one, I would have to multiply x to both sides, and I get x tangent of 55 is equal to 29. Then I would have to divide the tangent of 55 over to the other side. This means that x is equal to 29 divided by the tangent of 55. Once you have your equation set up for x, we're going to go to the calculator now and work that out. 29, divided by tangent of 55. And that's going to equal to 20.3, since we are rounding to the nearest tenth. Now we're going to come over here. Here's my angle 47. What we are given is x, which is the hypotenuse, since it is the side directly across, and then the 28 would be my adjacent, since it is next to my angle. The trig function that uses the adjacent and the hypotenuse is cosine. So my equation would be the cosine of 47 is going to equal to the adjacent 28 over x. Multiply x to both sides, and we get x cosine of 47 is equal to 28. Then you divide the cosine of 47, and we get that x is equal to 28 over 47. So now I'm going to put that into my calculator. And I get the answer of 41.05. And since I'm rounding to the nearest tenth, that would be 41.1. And this would be my answer. Now, just a side note, let's say, for example, this here was the 28, and this here was the x. Then it would still be cosine, right? So it'd be the cosine of 47, but instead of 28 over x, it would be x over 28. So if you wanted to solve for x, you would just multiply 28 to both sides. Whatever is in the denominator, that's what you multiply. And this is actually shorter. This would give me x is equal to 28 times the cosine of 47. And then you would go to your calculator, put 28 times the cosine of 47, and you would get that x is equal to 19.1. So that's the different ways that you may see these equations. Now for this final question, would you be able to find the third side length with this information? And if so, how? And the answer to that is yes. As long as you have two sides, you would be able to use the Pythagorean theorem. And then you can find that third and final side. And that's our intro to trigonometry.